what I did was I used another learning algorithm, an algorithm that can perform clustering. So what I did was I picked up the payloads, I clustered the payloads, I used the classification of the payloads as an input to the unsupervised learning algorithm for time series. And what I had was a two-stage process that meaningfully picks up packets, transforms the packets into a real time series, and looks at the time series looking for problems. So what happens is, and this is the idea, so what happens is that there are a number of results that show that, for instance, you can recognize protocols through neural algorithms. So if you give some packets from mixed protocols to a clustering algorithm, the algorithm can separate the different protocols without you teaching it the protocols, without you giving it examples, because they are structurally different. Of course, this is not perfect. Some protocols are similar, and those protocols will end up in the same cluster. But what happens is that, for instance, if you look at two very different protocols, HTTP requests and FTP commands, they are classified in totally different and totally separated classes. So what about the attacks? Let's pick up, once again, the HTTP protocol. And let's try a number of attacks against the HTTP protocol, against not the HTTP protocol itself, but for instance, against various HTTP daemons, against various web applications. Let's look at the attacks that can be carried over HTTP. So attacks are orange. No, sorry, normal traffic is orange. Attacks are blue. As you can see, the same unsupervised algorithm, which has separated HTTP traffic from other types of traffic, separates in a similar way most of the attacks in this particular and lucky example of the HTTP, all the attacks in other protocols, of course, which I won't show you because they are less impressive. It works not so well. But in most protocols, many attacks can be separated just by looking at the statistical properties of the payloads, which is different from the normal traffic. This does not work. For instance, an example of protocol where this will never work is any encrypted protocol. But no intrusion detection system can catch anything in the encrypted portion of protocols, so that's not just my problem, it's a problem of the industry. So what are the results? The results here are that we have a detection rate which ranges by standard tests above 70%, with a false positive rate of 0.03%. If that seems low, please remember that this is counted in number of packets. So that's not low at all. But in order for you to understand how much better this is than traditional systems, the best rating traditional system working just on the headers can find about 50% of the attacks with a false positive rate that ranges between 0.1 and 1%. So from 1 to 2 order of magnitudes more false positives and less true positives. This is already implemented in a GPL plugin for Snort. Why I'm not releasing it? It's because I'm not satisfied with it. And it's because I don't have the time to support it. So I already know that the day that I put it on my web page for download, I will begin to receive thousands of email support requests, which I cannot handle, which is why you won't find it for download. But if you want it for your own experiments, not that I'm restricting you because it's a GPL, you can then share it, but if you want it for your own experiments, provided that you agree that I will not support you, then just ask me for it. I can share it with you. We have done research in the host-based area. Basically, there's a bunch of ways for doing host-based intrusion detection systems. There's log-based intrusion detection systems. You can look at Daniel Sid's OSSEC for an excellent example of how you can do that. But usually, in the academic area, when you talk about host-based intrusion detection, most of the papers traditionally have worked on the characterization of system calls, because system calls are one of the ways to identify process behavior across different types of processes. All the processes that can violate the security of your system execute system calls, at some point, at least. The interesting part here is that usually people look at the sequence of the system calls and at their frequency, but not at the content of the arguments, which is exactly the same problem that we solved for network traffic by applying the two stages process. So we thought, why not to apply the same idea which worked once also to this type of stuff? And what we did was to look at the time series of system calls. We found out that it was very, very different from the time series of packets. And in particular, this is very well modeled by Markov chain models. This is nothing new. I will not spend much time here. If you want, we can talk about it afterwards, because it's been done a number of times. And when I say a number, I mean that if you look for Markov chain anomaly detection system calls, you will find thousands and thousands of papers that talk about this, but always about the sequence. What we did was to bring in, sorry, I don't have time to explain what a Markov chain is. We brought in the idea of looking also at the content of the chain. And how did we do it? It was through an idea which originally came from a professor who has graduated from my university and is now working at UCSB, University of California, Santa Barbara, which besides being a much richer university, is much closer to the sea, and it allows you to do surf after you taught lessons, which is something that you really cannot do in Milan, for fairly obvious reasons. Basically, Giovanni Vigna, with other researchers, developed a system which he called syscall anomaly, which was the first attempt in the world to look at the contents of system calls for anomaly detection. And he developed some very simple models, string length, character distribution, structure of the strings, and inference, in order to deal with anomaly detection. Theoretically, everything was very interesting, but when I actually proved it, and it was not done, you know, as a competitive thing. I was working with Giovanni. When I tried it, what turned out was that each model could be improved. And so, of course, someone, yours truly, improved the models. But besides improving each model, so besides modeling better the various parameters, what I realized was that there was a relationship between the various parameters. So let's give you an example that everyone who is proficient with Unix will probably understand. The most commonly called system call in a Unix program is an open system call. You may have programs that run as much as 95, 98, 100% statistically of their system calls as opens, because open is used for doing basically everything. Trouble is, how do you distinguish between an open being used to read libraries and an open being used to write to a temporary file and an open being used to read /etc/passwd? They're all opens, right? And if you build up a model which comprises all of these things, it will be just too large. It will encompass everything. So it will not detect anomalies. So what we did was to add a step of correlation among the various parameters of a single system call. So we basically created an algorithm which is able to divide your open system calls into various types of open system calls, based on the types of files that they are accessing, based on the permissions that they are using, so that you can actually model the open system call for libraries, the open system call that is used for the particular data file of that particular program, the open system call, how it's used by that program to access the TMP directory. And all of this, I would like to remind you, is done in a supervised manner, which means that I do not rewrite this application or write rules specific to each single program. They are just extracted from a number of runs of the program. So basically, you have to run a program like this in learning mode for a longer time, where it catches all the nuances of the uses of the programs on the machine. You have to create the structure, and then you can use it to detect new anomalies that happen on your machine. This is an example. I'm trying to shorten the presentation because I prefer to take your Q&A and leave the slides to you afterwards to study and to read than to spend my time commenting the slides and then having to run away from the stage. So basically what happens is that if you take the opens in FD format, which is basically the simplest Unix utility you can find, what you have is a bunch of opens that open libraries. Then there's a couple of opens that open devices. And there's a single open which opens a locale file. If you run our algorithm on this sequence of calls, what happens is that those calls that are in blue right now are collected together because they have the same prefix and they are opened with the same modes. These two are collected together for the same reason. And afterwards, the last call to libraries, which was slightly different from the other ones, is added into that cluster because it's still more similar to the other libraries than to the other things. So what you end up with is that your learning system, instead of having to learn the characteristics of all these bunch of files together, can learn separately the characteristics of the 3 different types of open that you have. And then you can apply the techniques that have been used and abused in the literature for creating, training, and detecting intrusions over a Markov chain. But instead of building a Markov chain where open is a single node, you have a single state. You have a Markov chain where each type of open is a different state. So if you go from one type of open to another type of open, which is still an open, but is totally different from what you would expect at that point, you will still see an anomaly, which is something that you will not see in the regular anomaly detectors. So basically, what we are left with are a system which detects host-based intrusions, which detects intrusions host-based, a network-based system which detects intrusions, and we are left with the joys of correlation, which you probably already know if you work in this field. As you know, probably, there's a number of products that correlate your alerts and your logs together. They already suck by themselves. But the biggest problem is that most of these products work using classifications of the attacks or types of log events. When you're working with anomaly-based detectors, you don't have types of events. You just have events. So you cannot use the type of event to correlate different things together. And you have to figure out ways, statistical ways, to correlate things that are significant